Right this very second, your body loses millions of microscopic cells to natural decay, routine damage, and physical exhaustion. In a healthy adult, the body must produce between 100 billion and 1 trillion new cells every day. Without this constant replacement, short-lived immune cells would vanish first, leaving the system defenseless against the most common environmental pathogens. To prevent this decline, the body relies on the hematopoietic system. Deep inside the cavities of our ribs, pelvis, and sternum, the marrow operates as a hyper-regulated biological manufacturing plant. Human survival relies on this continuous rescue mission, executing silently in the dark spaces of our skeleton. Every one of the specialized blood cells required daily originates from a single source, the hematopoietic stem cell. Notice the physical morphology of these dividing precursor cells. The distinct pinkish bodies and central dark nuclei are the hallmarks of this microscopic origin point. When a hematopoietic stem cell divides, it performs a precise mechanism known as asymmetric division. One daughter cell commits to becoming a specialized worker, while the other remains an unspecialized, exact clone of the original stem cell. Because at least one daughter cell always retains its stem cell status, the starting pool in the marrow is never depleted, no matter how many millions of times the replication cycle repeats. This division mechanism allows a small, finite reservoir of stem cells to maintain the body's massive cellular output for an entire lifetime. Once a newly minted progenitor cell leaves the stem cell pool, it faces a strict biological fork, entering one of two highly specialized assembly lines. The first path is the myeloid lineage. This is the heavy industry sector of the marrow, responsible for mass-producing red blood cells and the fragments required for clotting. The second path is the lymphoid lineage. This is the precision defense sector, dedicated to engineering targeted immune cells. Every piece of our physiological and immunological infrastructure is built downward from this initial cellular split. The production rate on these lines is dictated by distant organs. When the kidneys detect a drop in systemic oxygen, they release the hormone erythropoietin, signaling the marrow to increase the output of red blood cells. To maximize its internal capacity for carrying hemoglobin, the rapidly developing cell shrinks and violently expels its own nucleus. This process happens around a central macrophage within an erythroblastic island. The central macrophage acts as a guide on the factory floor and consumes the expelled cellular debris to recycle iron. Stripped of its core, the cell collapses into a biconcave disc. This indented shape makes it flexible, allowing it to fold and squeeze through the narrowest capillaries in the body. By sacrificing its internal machinery and its ability to replicate, the red blood cell maximizes the volume available for oxygen transport. Back on the myeloid line, massive megakaryocytes fragment themselves, shedding thousands of pieces to create the platelets that seal our wounds. Meanwhile, millions of newly formed neutrophils and lymphocytes roll off the lymphoid line, programmed to hunt and neutralize foreign pathogens. These parallel assembly lines operate in a synchronized overdrive, pushing out cells to preempt microscopic threats before they take hold. Finished cells squeeze through the endothelium and burst into the fast-flowing circulatory river, beginning a patrol that lasts for their entire 120-day lifespan. But if hemoglobin concentrations drop below normal limits, the blood loses its oxygen-carrying capacity. This state, known as anemia, begins to starve the organs of their required fuel. The supply chain fails in one of three ways. The marrow stops producing enough cells, cells are destroyed prematurely, or acute loss of blood volume. In cases of severe bleeding, the internal factory cannot keep pace with the depletion. The patient relies on external medical intervention to survive. Our physiological stability depends on the uninterrupted volume and quality of the marrow's output. Over decades of cellular division, the system is subject to biological entropy. Copying errors accumulate within the stem cell pool. This chart shows the population distribution of stem cells over a human lifespan. By age 70, an average person harbors up to 1.4 million protein coding variants, a condition known as clonal hematopoiesis. If a mutation provides a survival advantage, it triggers an expansion. The mutated clone outcompetes healthy cells, dominating the bone marrow space. The engine that sustains human life also harbors the genetic errors that compromise our health. Right now, this immense manufacturing process is operating simultaneously across the bones of your skeleton. It runs continuously, producing billions of precisely engineered cells every day just to maintain a baseline of health. We are kept alive by a microscopic forge of creation and destruction that never sleeps, working against constant decay to keep the body functioning.